Hello everyone! Today I'm going to talk about matrix vector multiplication in parallel computing. I will cover the problem definition, the sequential and parallel approaches, and how performance is affected. So let's start with the problem. We want to compute the multiplication between a matrix A and a vector X, resulting in a new vector Y. So each element of Y is calculated by multiplying a row of the matrix by the vector and summing out the products, as you can see here. So each row of A generates one value in the result vector. So let's see the sequential approach. In the sequential approach, we use a simple double loop. For each row, we go through all columns, multiply, and accumulate the result. This has a time complexity of O(n) squared. It's simple and it does not require communication, but it becomes slow for large matrices. And you have the code here that I did. You can see it. We have 2 fours. So why parallelize? Because each row can be computed independently. This allows us to divide the work among multiple processors and reduce the total execution time. The goal is to make the computation faster by using parallelism. So now let's see some parallel strategies for matrix vector multiplication. In the row-wise partitioning, we divide the matrix by rows, as the name just said. So each process is responsible for computing a subset of rows of the result vector. For example, process P0 computes the first rows, P1 the next ones, P2 the next twos, and so on. So this is very simple because each process can compute its part independently. However, there is an important issue. To compute any row, we need the entire vector x. So even if process starts with only part of the vector, we must send the full vector to all process. This is done using a broadcast operation. So while computation is well distributed, communication can become expensive. Now the second, the column-wise strategy. Instead of dividing rows, we divide columns, as the name says. So each process is responsible for a subset of columns in the matrix. Now, instead of computing full results, each process computes partial contributions to every element of the result vector. So each process produces a partial vector. At the end, we combine all these partial results to get the final vector y. This is done using a reduction operation. So in this strategy, communication happens at the end when we sum all partial results. Compared to row-wise, we avoid broadcasting. We avoid broadcasting the entire vector, but we introduce a reduction step. Now the third one, the 2D strategy. We divide the matrix into blocks instead of rows and columns. So each process works on a submatrix. As you can see in the example, the matrix A is divided in these blocks, and I painted with color so you can visualize it. So this means both the computation and the data are more evenly distributed. Now, instead of sending the entire vector to all process, we split the vector into parts. And each part is shared only among a subset of process, usually within the same column of the process grid. Then, each process performs its local computation using its block of the matrix and the corresponding part of the vector. After that, partial results are combined across processes in the same row using a reduction. This approach reduces global communication and replaces it with smaller, localized communication steps. That's why it's more scalable and efficient for larger systems. So the way we distribute data depends on the strategy. In row-wise, process receives rows of the matrix and eventually the full vector. In column-wise, they receive columns and parts of the vector. In 2D partitioning, each process gets a block of the matrix and part of the vector. This distribution has a direct impact on performance. So, there are different communications patterns involved. Broadcast sends data from one process to all others. Reduction combines partial results. All-to-all communication is more expensive because every process exchanges data. And in 2D partitioning, we often use local communication between neighboring processes. Which is more efficient? Now let's see the performance impact. So when analyzing performance, we need to consider communication cost, load balancing, and data movement. Even if the computation is perfectly parallelized, excessive communication can limit performance. So the best strategy is not just the one that divides the work evenly, but the ones that minimize communication. So here we have the comparison. The row-wise has high communication and medium scalability. The column-wise has medium communication and medium scalability. The 2D has low communication and high scalability. So, the main bottleneck in parallel computing is communication. In many cases, communication is more expensive than computation. That's why the best strategies are the ones that minimize data transfer. That's why 2D partitioning is usually the best choice, because it has less communication and better scalability, as we saw here. And that's it. In conclusion, matrix vector multiplication is a simple but fundamental problem. Parallelization can significantly improve performance, but the chosen strategy is critical. Efficient solutions depend on good data distribution and minimizing communication. That's it for today. Thank you for watching. Bye bye.